prime of x multiplied by f prime of x. So now I know that v prime of 1 will be g prime of f of 1 multiplied by f prime of 1. So first, let's identify from the graph f of 1. So I look at the graph. F is in red, and I want to determine f of 1. So f of 1 appears to be 2, correct. So then this is 2. Now, f prime of 1 is the slope of the tangent line to the graph of f at 1. So it happens that this is a linear function, right? So at any point here, there is the same slope. So I have rise over 1.
2.
So 4 divided by 2, and it's positive. Very good. So then this is also 2. So at this point, I have g prime of 2 times 2, which is f prime of 1. So I have to determine this. So this is the rate, the slope of the tangent line to the graph of g when x is 2. And g is in blue.
2.
So when x is 2, right here, what is the slope?
2 over 3.
So,
It's 0.
so this is g prime of 2. What does the function have at 2?
What's that corner?
So how much is g prime at 2? Does not exist. Because you can say, which one? The one on the left or the one on the right? So undefined. Very good. Anything else? That's why I keep repeating, what did I say all the time, or do I say all the time, that a function is differentiable if continuous and does not have
Corner or vertical tangent.
wonderful. Good. Other questions for me? Anything else? I do have a little bit of a leftover from 3.4 and a little bit of leftover from 3.5, and then we can continue. Anything else? Anything else you worked on? Okay. So let's go back to e to the x. And we know that e to the x prime is very good. Also, we know that e to a function prime, they normally use u of x, but I like to use f. What is this?
Even the function.
Times f.
Very good. This is the chain rule. So the inner function is f and the outer function is e. So e to a function prime is e to a function times f prime. Good. So now there is a property that for some reason we don't really emphasize it enough in pre-calculus that I need to use now for a particular reason. So here it is. Can I rewrite a, it's not e, anything else but e, to the x power? Can I rewrite this as being e raised to natural log of a to x? And don't say yes or no. Let me talk about the property a little bit. So anytime I have a base raised to log base a of x, as long as this and this are the same, the answer is x. This is one of the properties of exponential log, if you want, combined. We don't really talk a lot about this function, about this property in pre-calculus. Why? It's because we really address it again here. Okay. So therefore, using this property in which I have the same base here with the same base here. This is natural log. The base of natural log is e, like I have a and a. Then the answer would be a to the x. So that's how I got this. Now, what am I after? I am after this prime. That's what I'm trying to find. So I'm going to differentiate this in order to get this. However, this expression, right, there is another property of the exponentials, of the log, which is log base in any base of x to the b power. The power goes in front as a factor. So this is b log in any base you want, let's say a, of x. So I am going to differentiate both sides in order to determine this. So let's differentiate. But after we apply this property here. So a to the x is e raised to x natural log e. Is this clear?
Did you mean that?
The natural log a. I'm sorry. I think I said e. I'm sorry. I didn't mean that. So are we in agreement with this? And then are we in agreement with this?
Yes.
Because if you say yes, then we will be able to discover a to x prime, which is totally different than e to x prime. So if the base of the exponential function is e, then we move forward as planned. But if it's not e, it's anything else. There is a different formula for that. And we are going to develop it right now. So using implicit differentiation, knowing that the left-hand side equals the right-hand side, that's why I didn't want to talk about it in 3.4 before doing 3.5. Okay, so the left-hand side is a to the x prime. And now, what is the right-hand side? So this is e to a function. So when I differentiate e to a function prime, I have e to that function multiplied by the inner function prime. Natural log a is 15, right? So when I differentiate this is a linear function, a constant times x. So when I differentiate this, what do I get? So now, remember what we said, that e raised to natural log a to x is, or e raised to x natural log a to x, a natural log a was this. I'm going to replace it here. So this is the same with this, but this is the same with this. So the answer is a to the x prime equals a to the x natural log a. What if I change a into e? What will I get? Because natural log e is? Natural log e is 1. So this is in the case in which the base is not e. Now what if I have a to a function prime? What will I get?
Times f prime.
Natural log a.
Right? Does it make sense?
Yeah.
Good. Any questions? And I do have a little bit of a leftover from 3.5. And I only need 3 things from you. So from back to 3.5 for a moment. And let's talk about inverse, trig, functions. You will not be able to live in Calc 2 without these 3 functions. There is no life in Calc 2 without these 2. So here's one, sine inverse x, cosine inverse x, and tangent inverse x, and this is the one that I tortured you with from the very beginning, right? This is the arc tangent x. We looked at the graph, we applied limits to it, so the graph is committed to memory, the asymptotes of the graph are committed to memory, and this is the derivative now. So when we differentiate sine inverse, the answer is 1 over the square root of 1 minus x squared. When we differentiate cosine inverse prime, we get the same thing but with minus in front. And when we differentiate arctangent or tangent inverse, we get this. I don't like asking you to memorize, but we need these three memorized. And now we can practice a couple of problems with this. So on page 216, I'm not interested in anything else. The formulas can be given to you. I'm not gonna. These are the three that I need. Anything that has these three, 49 through 60 on page 216. 49 through 60 on 216. So let's differentiate a couple of them. For example, I can suggest 54. I'll suggest, let's say, or 53. I suggest 53. I suggest 57.
Let's do 53.
Let's do 53. We are given a function that is uppercase G, the square root of 1 minus x squared multiplied by cosine inverse or arc cosine. So please get used to both notations. You know I'm lazy. I will not put the power. I will write arc cosine because it's easier. So both mean the same thing. So g prime of x. I have to look at the function, and in my head, if you want, decompose it in pieces. So what does this function mean? What is it? It's a.
Wait. It's like square root of 1 minus x squared times.
It's one function. And cosine inverse is? Right, correct. Product. It's a product. So this is the first function, and this is the second function. If you're using my method, then you will say y prime, 1 prime times 2 plus 1 times 2 prime. You can twist them the way you like. That's fine. With the product. But with a ratio, be very careful. Okay, so when I differentiate a square root of a function,
So 1/2
very good,
square root of 1 minus x squared.
times the inner function prime.
2x.
Okay. Correct. Now I copy the second function. Plus, I copy the first fraction, not fraction, but function, and multiply by the derivative of cosine inverse, which is negative. Do not forget to put parentheses, because otherwise you may forget about the product. 1 over the square root of 1 minus x squared. And yes, we can simplify it a little bit. I will divide by 2. Yes, I can simplify these two. However, I don't see a point because I still have the same denominator again. So I'm just going to write a long fraction line, the square root of 1 minus x squared. Both terms will be negative. So I'll put a minus in front. The top of the first one is x cosine inverse. And the top of the second one is positive x, of course, plus 1. So one more time, I took the minus in front as well as this one. I did not simplify these two quantities because I noticed that there is the same denominator here. So if they have the same denominator is even better. So the top was x cosine inverse plus, because this minus is right here. Yeah, I'm sorry, yes, in my head, see? Okay, so there is nothing else we can do here. This is it. That's how we differentiate functions that have inverse trig functions in them. Should we look at one more? Okay. What about 57?
So you couldn't cancel those two?
Yes,
squares?
yes. And I would have had this fraction plus 1.
Yep.
That's fine. If you want to do that, you can. So I'll say here or, and I simplify these two. So I have negative in front, x cosine inverse divided by the square root of 1 minus x squared, and then minus 1. However, this is good. I mean, full credit, right? But what I'm trying to prepare you for is for chapter 4, in which when I want to set this equal to 0, I'll have some difficulties. But if I set that one equal to 0, I know the numerator has to be 0. So here I'll have to add, subtract fractions.
Just scoot up just a hair.
Yeah.
I just want to bang it in my head. The negative 2x, because inside the square root, yep, okay. Just want to make sure.
Yes? So if I set this equal to 0, I will still have to change it into a fraction in order to solve. So again, in this particular situation, they are both correct, both acceptable. However, when we solve the equation this equals 0, then here I can't. I still have to find the least common denominator and add the fractions or subtract the fractions first.
Okay.
So that's why this is more useful. Okay, so we also said 57. 57 is y equals x sine inverse and then plus the square root of 1 minus x squared. We're asked to differentiate. You can write y prime. I think this is better, but it doesn't matter at this point. This is not implicit differentiation. So we have two functions, one that is a product of two functions and this one that is just a function composition. So in the product, I will differentiate the first and multiply by the second and plus x multiplied by the second function prime, which we know is the same with cosine inverse prime, but without the negative in front. So here I had to use the product rule, 1 prime times 2 plus 1 times 2 prime. And then plus, for this I know what I have to write is 1 over 2, the square root of 1 minus x squared multiplied by negative 2x. And this is quite nice because after I simplify the 2 with the 2, this becomes negative x over the square root, and I have a positive x over the square root. Therefore, the answer is,
Where does the plus x come from?
the first function prime is 1 times the second function plus the first function times the second function prime
So
plus this function prime, 1 over 2 the square root times the inner function prime. So it happens that this x over with the minus x over will go away. So the answer is just sine inverse. Is this better? And this completes the sections 3.4 and 3.5. I had just those two pieces to explain how to differentiate. Yes, please.
So we just need to go sine, cosine, and
Inverse.
the inverse.
Yes, all the trig functions, which are 6,
Mhm.
but the derivative is only of 3 inverse functions,
Got it.
because these will follow you in Calc 2. The other ones.
I remember I had to learn all six before, and I was just
No, just for the inverse functions, just sine inverse, cosine inverse, tangent inverse. Now, if I put something on a test, I'll give you the formula, which is not going to happen. I'm testing basic information that we can build on. Yes, Stephen?
So I guess I'm confused where the 1 over the square root of 1 minus x squared came from.
You're saying this one?
Yes.
Okay.
Oh, okay.
So let's do this again. So the first function prime is 1 times the second function plus the first function times the second function prime plus this function prime, which you already did a minute ago, 1 over 2 the square root times the inner function prime. So after I simplify 2 with 2, this quantity becomes negative x over this, but this quantity is positive x over this. So that's why these two go away. And the simplified form is sine inverse. Better?
Yeah.
Other questions? Other questions? Okay, so the plan for today is moving forward to look at 3.6, which deals with log functions. You thought you could get away from log? No, you can't. And if possible, that part I don't know. There is a lot of work in this section. If possible, move on to 3.7. We'll see. Okay. Here's our function f of x equals natural log x. The derivative of this function is something that it didn't have a place anywhere else. It's 1 over x. What if I have natural log of a function prime? What do I get?
1 over x. Or 1.
I should have multiplied here by x prime, but I don't because that is 1. Okay? One more. Let's discuss this one. Log base a of x. Totally different story. How come? Because this one has base and this one has base a, which means, if you remember, we had a totally different situation when we differentiated e to the x, which was this, and when we differentiate this, which is a to the x times natural log a. So something must be different here. When we differentiate natural log or any other base, something will be different. And here it is. I'm sure you remember there is a property, I should say the change of base formula for logs. So if I want to find log base 7 of 3, assuming we don't have base 7 in the calculator, the more sophisticated ones do, but I do have, let's say, natural log. So then this is natural log 3, everything divided by natural log 7. So any log you give me, I can change it into natural log. I'm going to do that here. So can anyone tell us how to write this using the change of base formula?
Log x over log a.
Very good. So now let's differentiate. Exactly. Now let's differentiate. Remember, natural log a is a constant. It goes outside. 1 over natural log a. And times natural log x prime, which is? So the answer is this. So when we differentiate log in any base, it's not just 1 over x, but it's 1 over x times natural log a. And now, of course, let's put, instead of x, let's put in a function And what would you say for log base A of a function prime? Yes, please.
One over natural log A times 1 over F times F prime.
Perfect. Awesome. So this is basically F prime divided by F times natural log A. Very good. Perfect. Okay. I would like to look at some problems. Let's say we're on page 223. For now, let's pick anything between 2 and 22. On page 223.
On page 223?
223. Okay, you choose next. I already chosen. F of x equals natural log of natural log x. Okay, so we're asked to find f prime. So please get the next question ready when you can. So we're asked to find f prime
What's that natural log times natural log?
of, there is no natural log without an argument. Since it's natural log, it really means this. Natural log applied to natural log. Perfect. Okay. So we have an outer and we have an inner. So let's differentiate. We first differentiate the outer, and you don't care what this is. We differentiate the outer. What do I have? No, 1 over the whatever. Okay. 1 over natural log x times the inner function prime. 1 over x. So this is 1 over x natural log x. Okay, please choose or I will.
Choose that one. Natural log F.
Okay. What about 11? Any questions? G of x equals natural log x, the square root of x squared minus 1. So natural log applied to a product.
It's the first part, 1 over x times.
You mean here or here?
Oh, number 11. Yeah.
Okay, let me show something and then I'll ask you questions. Do we remember the product rule for logs? Let's say log in any base of a multiplied by b. What does this equal to? Very good. Plus log b indeed. It's the sum of the logs. Good. I would like to do that here. You can say why. Well, we can go back and do it without applying the property of the logs, and you will see what happens.
No, that would be log or natural log x plus natural log x or the square root of x squared.
Good. Now there is a property of the logs that allows us to take the power in front as a factor. There is nothing I can do here, but there is something I can do here. So this is why we did this in pre-calc. Condensing and expanding logarithmic expressions. So this will become natural log x plus 1/2 natural log x squared minus 1. And you can say, what's with all this preparation? Because I want to show you one of applications of log, basically a property, in this case two different properties that we applied to simplify the function. So now g prime of x is easier to calculate. Why is it easier? Because I don't have to use a product. And I can do this for everything. I can apply natural log to both sides of a function. And I'll show you what happens in a minute. So this prime is 1 over x. 1/2 is 1/2. Now here I have no choice. I have to write 1 over x squared minus 1 and multiply by 2x. And this is so much easier than going back there and differentiating log of a product. I will simplify a little bit, and then I get 1 divided by x plus x divided by x squared minus 1. And let's say we leave it as is. Would you like to see the other way?
Sure.
Yes? Okay, well, g prime of x is natural log of a function, which will be 1 over x, the square root of x squared minus 1. And now I have to use the product rule. The first function prime is 1 times the square root of x squared minus 1, and then plus the first function times the second function prime. So this is x divided by 2, the square root of x squared minus 1, and multiplied by 2x. You can say, and I would have to agree with you, well, this is not as difficult. You could have done this. True. But the simple radical, is, this is much easier to work with than this. So in here, I will have to find the least common denominator after I simplify. I copy the first portion. The least common denominator is the square root of x squared minus 1, which needs to be multiplied by the top here. So plus x squared. So this is x squared minus 1 plus x squared. Eventually, I have to get the same thing. So this is 2x squared minus 1. And this is x times x squared minus 1. And this is exactly what I determine here with the least common denominator. X times x squared minus 1. This needs an x squared minus 1, and this one needs an x. So it's going to be x squared minus 1 plus x squared. But I think that the prep and the simplification using log, it's much easier than going through this process. Any questions? In certain situations, we have no choice. Here I had two paths. One, applying properties of log to simplify the function as much as possible. I couldn't go beyond this. This was the simplest. And the other path is to differentiate the function as is. However, there are situations in which we cannot differentiate before we apply log to both sides. There is no way we can differentiate a function that I'm going to talk about right now. And I'll let you choose, actually. The process is called logarithmic. What do you think?
Great.
Differentiation, of course. Of course, logarithmic differentiation, that's what it is. Now the question is, when am I forced? And I have no choice. When am I forced to use this? Here's when I'm forced. Say it again.
When you send your directions.
No. No. So when I have a function raised to another function. So if I have a function raised to another function, I will say no rule, comma, just log differentiation. There is no rule for differentiating a function raised to another function. E raised to f is not a function raised to another function. It's a constant raised to another function. Here I'm talking about a situation like this. And you can choose if you want 43 through 50.
43.
43 through 50, page 223. And we said 43. Y equals x raised to x. I know how to differentiate x to the 5th power. Bring the power in front and subtract 1 from the power. But a function raised to another function has no rule. I have to apply natural log to both sides. Natural log to this side and natural log to this side. The left-hand side is natural log y. But can anyone apply a property and simplify the right-hand side a little bit?
The natural log.
So what do I write? Instead of natural log of x raised to x. Very good. The power goes in front as a factor. And this I know how to differentiate. But I had to apply natural log to both sides. And now the question is, who cares about your natural log y? I will still be able to determine y prime. I'm after y prime. I'm after y prime. I apply log, I differentiate, and then I'll show you what happens. And we will still be able to determine an expression for y prime. But no rule is applicable here. So I differentiate now the left-hand side, and I differentiate the right-hand side. When I differentiate the left-hand side, I get, remember, y is a function.
1 over y times 1.
So natural log y prime is 1 over the function times the function prime. But we don't want to use y prime.
Yeah.
It's not wrong. You will get full credit if you choose to do that, but I don't recommend it. Now the right-hand side is a product. When I differentiate x, I get 1 multiplied by natural log plus. I keep x, but I differentiate, okay. You cannot continue to the left or to the right to further simplify. This is an equation. Be very careful. So we only have one left-hand side, the equal symbol, one right-hand side. You cannot continue right here and simplify it. Be very careful with that, because you're going to lose track of which one is the left-hand side and which one is the right-hand side. This is an equation. Okay, so the left-hand side is 1 over y dy over dx. I am after this. What should I do to both sides? I'll simplify the right in a minute. What should I do to both sides of this equation to solve for this?
Multiply by y.
That's it. And that's how I get dy over dx. dy over dx equals, instead of writing y, I'm going to write x raised to x. And now please tell me what is left in parentheses. And that will be natural log x plus. So we are not losing anything by applying natural log to both sides. We can still find an expression for y prime. But we could not have done this directly.
What happened to the y?
I multiply both sides by y, but I don't want to write y. I wrote x to the x.
Does it always work out that way?
Because y is the beginning equation is y.
So when you multiply this side by y, y disappears, and then you multiply this side by y. To multiply both sides by y. Is that better?
Not really.
Okay. So I multiply the left-hand side by y over 1. I multiply the right-hand side by y. Y with y will go away,
Yeah.
and I only have
Yeah,
dy.
I get that part.
Okay. Y is x to x. So I put it in front.
And then the x times whatever x makes.
Is 1.
Okay.
So this is this, and this is this. Better?
If you leave y,
Say it again.
if you leave y, is that wrong?
No, it's not, but very good question. But when I present dy over dx, I have to have an expression in x, unless I don't have y. If I don't have y, then I will have to keep it as y, like the implicit differentiation. But if I shouldn't have x and y in an expression at the same time, unless I don't have y. But I do have y, which is x to the x. So as you see, all this expression has only one variable. If I keep the y, then I'll have 2. Now, if I don't have y for some reason, who knows what happened, then it's a different story. Then I have to keep them. Otherwise, I have to. Okay, let me choose. Let's make one up. So let's say sine x raised to cosine x. There is no rule for a function raised to a function. I can still find an expression for this function's derivative, but there is no rule. What is my only chance? My only chance is to denote first. That's my first step. Denote this by y. My second step must be,
Natural log.
very good, natural log y equals cosine x times natural log sine x, because I already brought the power in front as a factor. And now, keep it as an equation. This is not an expression. I differentiate the left and I differentiate the right. Also, keep in mind the fact that y is a function. So what do we get on the left?
1 over y times dy dx.
Now we have to be careful on the right-hand side because this is a product of two functions. This is the first function and this is the second function. The first one prime is
Negative sine x.
times natural log sine x and then plus. Now I keep cosine x and multiply by natural log sine x prime, which is
1 over sine x.
times sine x prime, cosine. Do we need to do this one more time or?
Yes.
Okay, very good. So we have y equals sine raised to cosine. I applied natural log to this side. I applied natural log to this side, and the fact that the power becomes a factor in front of the log. Is this clear? Yes? Everyone? Okay. I differentiate the left-hand side, keeping in mind that y is a function of x. So when I differentiate log of a function, I have to write 1 over the function times the function prime. Is that okay? Now the right-hand side. This is a product of two functions. I differentiate cosine first and I get negative sine times the second function, then plus. I copy the first function, but I have to differentiate the second one. It's the outer and the inner. When I differentiate the outer, I get 1 over sine x. And then when I differentiate the inner, I get cosine x. Is that better?
So when you have like the natural log sine x, are you essentially recreating the 1 and 2 function again?
Yes.
Yes. So
Okay.
this is the f and this is the g.
Okay.
So natural log of a function is 1 over the function, and then times the inner function prime.
1 and 2 inside of 2.
Exactly. F of, yes,
Okay.
exactly. Okay, we're going to try to simplify a little bit. So I have 1 over y dy over dx equals. There is nothing I can do to the first term. Here's what I would like to do to the second term. Because this is a function, ladies, because this is a function that is what? I'm asking about cosine divided by sine. Cotangent. So that I eliminate the fraction. So that I eliminate the fraction so I don't have fractions in there. And now the final step is to find dy over dx. What should I do to both sides? Please remember this is an equation. You cannot simplify to the sides. So then dy over dx, what do I do?
Bring down what y equals before.
Multiply both sides by y.
Well, yes.
So instead of y, I'm going to write sine x raised to cosine x. And then in parentheses, brackets, whatever you want, it's negative sine x times natural log sine x. And then plus, of course, you know, I always run out of room, cosine x times cotangent x. I'm going to erase that. So this is logarithmic differentiation. I can use logarithmic differentiation in other situations as well. But in a situation like this, I'm absolutely forced to use it because there is no rule for a function raised to another function. Any questions? That's the final answer. Would you like to practice anything else? Because I would like to show you one other important thing here. Would you like to practice? Now we can say anything from 2 to 32, and 33 and 34 as well, 39 through 50.
40.
Page 223. Is 49 okay, or you want something else? Which one? Okay. Did you say something else? I'm sorry.
Oh no, I was saying that sounds fine.
Okay, so 49, y equals tangent x raised to 1 over x. You notice here that there is a function raised to another function. We're not talking about product of functions, although I can use logarithmic differentiation for products as well. But this is not a product. This is a function raised to another function. And there is no other way but, yes, apply natural log to the left-hand side, and then the right-hand side will be 1 over x times. Do we agree with this? Okay. Now, I have two options, and sometimes we will we'll consider this option. I can say that I'm going to differentiate a product, this and this, or I can say I'm differentiating a quotient, this over this. Okay. So let's differentiate the left-hand side and differentiate the right-hand side. The answer will be the same. There is no question about it, no doubt. Okay, the left-hand side is
1 over y, dy, dx.
very good, equals. Now remember, we committed to memory this one, 1 over x prime. And this is very important because otherwise we will always have to start from scratch. It's x to negative 1 and differentiate and differentiate. So we committed this to memory that 1 over x prime is negative 1 over 1 over x squared times natural log of tangent x and plus 1 over x times 1 over tangent x times the inner function prime, which is, remember, tangent goes together with, exactly. Always remember, tangent and secant are very good friends. Cotangent and cosecant are very good friends. And there are equations in which only cosine and only secant and tangent are present. There's another equation that only cotangent and cosecant is present. So they go together, hand in hand. Okay, so all I would like to do here is just solve for dy over dx. Yes, you can factor out 1 over x. No, there is no need in this particular problem. So dy over dx equals, I multiply both sides by y, but I'm going to write tangent x raised to 1 over x, and then I copy the rest. And I'm going to copy these two fractions because it will be easier. So negative natural log tangent x over x squared, and then plus secant squared over x tangent x. And that's final. Any questions? Any questions? How many different, let me